Okay. Let's talk about Saturn. Can you open your books to page 203, section 7.5? How about you, Leah?
Yes.
Don't want to get involved?
I would like to.
Very nice. My little clicker. Whoa.
Whoa.
Sorry.
Wow.
Thank you.
All right. What about Saturn? Saturn looks different than Jupiter. Why is that? Well, Saturn is actually made of the same stuff Jupiter is. Pretty much. So Saturn also has bands like Jupiter. You know, zones and belts and such. But the bands are not as distinct. And the reason is there's two reasons. One, Saturn's internal temperature is lower, so there's less convection. See, Jupiter's bigger and has more gravity. And so it pulls in the gases real tight, and there's a lot of pressure down there, and it creates a lot of heat. Also, Jupiter's closer to the sun, so that makes it hotter too. And so the combination of that is a higher temperature, and when you have more temperature, you have more convection. Stuff is rising and falling faster. And so if you have more convection going on, you're going to get more distinct bands. So Jupiter has less convection and less distinct banding. Also, Saturn has weaker gravity than Jupiter. Saturn's much smaller than Jupiter as far as mass goes. And so Jupiter's upper layers of gases are squeezed in really tightly because of all the gravity. Saturn's upper layer of gases are more diffuse. They're not pulled in as tightly. There's not as much gravity. So when you're looking through the clouds, you can't see the different layers. They aren't close together. They're real wide apart from one another. And so you're only seeing, it's kind of hazy. It's hard to see down and see these different layers. So we do see bands on Saturn, but they're just not as distinct. This is what Saturn's layers are like. And it's the same as Jupiter's. There's an ammonia ice layer on top, below this haze layer that's pretty wide and kind of hard to see through. And below that, an ammonium hydrosulfide ice layer. This is the same thing that was on Jupiter. And a water ice layer. It's the same thing on Jupiter. So, it's the same layers, but they're a lot wider. If you look back at at the picture, the graph they showed you on Jupiter, look down here, the altitude in kilometers, the water ice goes all the way down to 300 kilometers below the surface. They consider this haze layer to be the surface. And so this water ice layer extends all the way 300 kilometers down. Go back to the one with Jupiter. Oh, there it is. And look at the water ice is only 100 kilometers down. So these layers are packed in close together on Jupiter. And on Saturn, they're more spread out. There we go, right there. Interesting. Saturn has bands that move much faster than on Jupiter, up to 1,500 kilometers per hour. And I can't remember what they said Jupiter's moved. Did anyone read about that? How fast it moved? Any idea? $800 kilometers per hour, maybe 700. So Saturn's might be twice as fast. I can't remember. Saturn also has storms that come and go, but don't last as long as the one on Jupiter.
It's 500.
500 kilometers per hour?
Yeah.
Good job, Olivia. So Saturn's bands are moving, winds are moving 3 times what Jupiter's are moving, and nobody knows why. Maybe you'll figure out why one day. That'll be your contribution to science. Carson. Will you call me when you get that figured out? Appreciate it. So there's a couple of storms on Saturn. And this is seen with an infrared picture. See the eye there? That means infrared. You can see the storms kind of circulating around. Here's some video footage. Saturn cloud rotation. Pretty lame. Oh, they're going to zoom in. Okay. It rotates. Saturn storm.
This is a view of the planet Saturn as seen in December 1994 when a large white storm erupted over the equatorial region.
It's also lame. I guess that's the large white storm. That's this big. Alright. What about Uranus and Neptune? Uranus and Neptune have high amounts of methane. Methane is blue. This causes the planets to be bluish, with Neptune the bluest because it has the most methane. So you get that dark blue color with Neptune. That's because of the extra methane. Why do Neptune and Uranus have more methane than Jupiter and Saturn? I do not know. Does that answer your question? It wasn't your question, it was my question. It's difficult to see through Uranus's thick outer atmosphere, thus it looks uniform. There is enough data to detect Uranus's rotation at 500 kilometers per hour. That's about what Jupiter was. Right, Olivia?
Right.
There's probably a good reason that Neptune and Uranus have more methane. But I don't know it. Maybe that's in the reading. Maybe not. I'll see it. Got all this? Yes? No? I'm turning.
Yes.
Getting an answer. This shows the rotation of Uranus These computer-enhanced Hubble Space Telescope images taken at roughly 4-hour intervals show the motion of a pair of bright clouds labeled A and B in the planet's southern hemisphere. The numbers at the top give the time of the photo. So that's one way they know it's rotating. You see these clouds here in their motion.
A large star, the Sun.
Alright, we aren't watching that. The clouds circle the planet at speeds of 500 kilometers per hour. This is a view of Uranus's ring. The ring is very thin and hard to see. This is shown with the infrared, and you can see it better in the infrared. Infrared is heat, remember. The fastest moving clouds, the fastest moving atmosphere is Neptune, 2,000 kilometers per hour. No one knows why Neptunes are so fast. There is some internal heating mechanism inside Neptune that's making the inside hot, a little bit hotter than you would predict it. Could be there's radioactive elements down there creating some heat. That's one thing that heats the inside of the Earth. Neptune had the Great Dark Spot, a huge storm like that of Jupiter, but it disappeared before the Hubble looked at it in 1996. I talked about this already. When Voyager 2 went past Neptune, it had this great dark spot. And Voyager 2 went past Neptune in the 80s, I think. And then when the Hubble came on board, they could take a good picture of Neptune, and the great dark spot was gone. So that storm, we know it didn't last. We know it disappeared sometime between when the Voyager passed it and when the Hubble came on. And there's the great dark spot. Which was thought to be a big storm also. Here's some other pictures taken, I'm assuming that's with the Hubble. These Hubble Space Telescope's view of Neptune were taken years apart when the planet was some 4.5 billion kilometers from Earth. The cloud features, mostly methane ice crystals, are tinted pink here because they were imaged in the infrared, but they are white in visible light. Notice that the great dark spot has disappeared. Okay. The next section, 7.6, talks about the interior of these planets. The gas of the Jovian planets becomes hot, dense, and liquid as you go deeper into the planets. So when you go deeper, you're getting more pressure. You're pushing these gases further together. So it goes from a gas to a liquid. It eventually becomes liquid metallic hydrogen, which is something that doesn't exist except in the middle of these huge planets. A semi-solid rocky core lies at the center of the Jovians. It's kind of like Earth at the center. And the cores are about 2 or 3 or 4 times as big as the Earth. So it's like it's got an Earth at the very center, a big rocky core. Surrounded by liquid metallic hydrogen. So here we have molecular hydrogen, that's just hydrogen gas. You go deeper, you have the metallic hydrogen, and deeper than that you have the rocky core, ice and rock. It's this metallic hydrogen swirling around that creates the huge Magneto Spheres. Yes? Yep.
This animation begins by showing the comparative sizes and colors of the Jovian planets. We can artistically take them apart, revealing their relative innards. All of these gas giant planets, especially Jupiter and Saturn, emit more radiation than they absorb, suggesting great heat within them. Jupiter and Saturn have very similar interiors of mostly hydrogen. Somewhat by contrast, Uranus and Neptune are also thought to have nearly identical structures and compositions.
The slush is the liquid metallic hydrogen. Mm-hmm. Yeah. There's an extra reading on page 208.
So if you fell through like Jupiter, assuming like you could withstand any amount of pressure, would you just like hit that core?
Eventually, yeah.
Okay.
You'd have to go through liquid metallic hydrogen that's at incredible heat. You'd be kind of swimming through that as you fell. Like falling through the ocean, I guess. Only way thicker and denser.
How can hydrogen be metallic?
Yeah, it can't unless you take it at huge pressures and push it together. And what a metal does, metals have the electrons of the atoms can move from one atom to another very easily. That's a property of metals. And so this happens when hydrogen atoms are pushed close together. You have that same property. That's why they call it metallic hydrogen. If you look on the periodic table, hydrogen is right there in line with the metals. But it's just so light that it's usually a gas. But if you make it a solid or a liquid, it'll take on those metallic properties.
Is it possible to make it a solid?
I guess if you pushed it together hard enough, but maybe the pressures inside Jupiter aren't even enough. What happens in the sun when the pressures get so great is the hydrogens fuse together, and you get this huge fusion reaction. So maybe not. Maybe if you push them hard enough, they just fuse, and they never become actually a solid.
Can you force anything to become metallic?
What's that?
Can you force anything to become metallic if you push it together hard enough?
I don't think so. I think it has to have the right electron structure, electron configuration. Remember the periodic table, like everything on the left is a metal, and then everything on the right is like a non-metal, or it's a chemistry thing. Maybe Miss B-Rad would know. This is an extra reading section about a comet that they saw hit Jupiter. The comet was orbiting around Jupiter and the Sun, and when the comet went past Jupiter, it got real close to it and it broke the comet up into little pieces. And then the next time by, the comet slammed into Jupiter. And each piece slammed into Jupiter. So each one of these is a piece of those comets. It slammed into Jupiter and made huge, like, explosion marks where the comet hit the atmosphere. And you think, well, it's a gas giant, the comet would just go right through and you wouldn't see anything. But because of the great speeds that these things are traveling, they'll even with gas, they'll impact it and make an explosion. And so they saw this comet hit. There's There's a view of the explosion. This is Jupiter. And there's the explosion on the surface. That explosion is many times the size of the Earth. So these are huge impacts. It's the only time any human being has ever witnessed an impact and lived to talk about it. That's pretty cool. You can read about it on page 208. Happened back in 1992. Or no, I'm sorry, 1994. And the astronomer who saw the comet breaking up, they named the comet after that astronomer. It was Shoemaker-Levy 9. And the astronomers did calculations and said, well, it's going to hit Jupiter the next time around. So they trained all the telescopes in the world on it to watch it happen. We've already seen this. The Magneto Spheres. When you have this spinning metallic hydrogen, you create huge magnetospheres. Jupiter has the strongest magnetic field, 20,000 times stronger than the Earth's. That's a strong magnetic field. And it's huge. It extends all the way through Saturn's orbit. So Saturn at some point goes through Jupiter's magnetic field as it's orbiting. Because of the field, Jupiter has vast aurora, more spectacular than those on Earth. Remember, the magnetic field traps solar wind particles from the sun and bends them into the north and south poles of the planet. So these solar wind particles come toward Jupiter and get caught in the magnetic field and go down in the north and south pole and create lights, light up the atmosphere there as the particles hit. And so those lights are real bright. As the crafts flew by Jupiter, you could see the real bright lights. And here you see a picture. There's Jupiter. And this purple is its magnetic field. The magnetic field is blown by the solar wind and shaped by the solar wind into what looks like a spearhead. And so it extends all the way out to Saturn's orbit. Saturn going around like this. Goes right through it. And when we launched this craft called Pioneer, it went through the magnetic field here, and sure enough, when it was right here, it didn't detect any solar wind particles. It was all being deflected by Jupiter's magnetic field, even way out here past Saturn.
What exactly is solar wind again?
Solar wind are protons and electrons coming off of the sun. The sun constantly blows out particles off of its surface, and they just fly through space in all directions. It's called the solar wind. And it's a pretty powerful force. If we didn't have a magnetosphere, it would impact us and kill us. I mean, it wouldn't be good. Did you see the joke I had up there the other day about we're only separated from certain death by a magnetosphere that's poorly understood? Anyway, it's pretty powerful, and that's one of the things we have to worry about if we ever go to Mars. Mars doesn't have a magnetosphere, so we wouldn't be protected from the solar wind, and it wouldn't kill you right away. It would kind of be like sitting and getting a sunburn real bad. You'd be impacted. It would microscopically impact your DNA and stuff and cause cancer and things. it's not good. So you can't withstand too much of those particles. Here's the bright aurorae seen on the north and south pole of Jupiter. I guess that's in the ultraviolet spectrum. The insets are.
It has visible, what if it has visible and ultraviolet?
Well, this part of the picture is visible, and this part of the picture is ultraviolet. Thank you. Yes. Yes. The other Jovians have magnetic fields, but they're not as strong. And they're often not along the rotation axis in all planets. Which is kind of weird. Our magnetic field extends along our rotation axis. So the magnetic field comes out of the North Pole and into the South Pole. But on some of these Jovians, the magnetic field will come out at the equator and come back in near the equator on the other side, or not directly north and south, and they don't know why that is. It must be something in the way the material in the middle is circulating differently than the winds are spinning the planet. But they show a figure right here. You can see Earth's magnetic poles are pretty close to the rotational poles, and so are Jupiter's. Magnetic axis in yellow, rotational axis in white. Saturn's pretty close. But look at Uranus. Rotational axis here, remember Uranus lays on its side. More anus jokes. But here's the magnetic axis at a 60-degree angle to the rotational axis. And Neptune's also at a big angle. Rotational axis, magnetic axis. So,
It's not even passing through center?
now, it's off center. Neptune rotates like that, and the magnetic axis is right there. Scientists don't know why. I already talked about internal heating. Okay, so finished reading chapter 7. We got a lab on Monday, and then Tuesday is astronomy, and the test was supposed to be Wednesday, but we aren't having school Wednesday, so I guess we're going to have to do it Thursday or Friday or someday.
Can I turn this off?
Yes. Is there a good day for y'all?